Yeah!
Hi, I'm Michelle Brasso. I'm a physics and earth and space science teacher teaching grade 9 through 12. I've got some great demonstrations and activities for your students with regards to circular motion. Some things that they can do, some things that you can demonstrate, and an experiment for them to connect to Jupiter's moons. Here are a few of my favorite activities to teach students about the direction of the acceleration, the force, and the instantaneous velocity in uniform circular motion. Here I have a hula hoop and a marble. What I'm going to do is spin the marble in the hula hoop, and I ask the students, when should I lift this hula hoop so that the marble knocks down the block of wood?
Okay, can you guys knock down the block?
It's got to be directly behind. As an angle.
No! What? Yo, what are you doing? Boom.
There you go.
Yay! Yeah! Did you get it? Go! Go! Yay!
Where'd the ball go? Speed.
Trajectory is equal to pi d.
It's a math term.
Yeah, because we're just that good, Lucas. We're just going our group.
Nice.
Oh, EJ! That doesn't count. That's what it's called. Yes, it does. Watch.
Alright, ready, release.
That meter stick.
Is the angle of... Whoops.
Yeah. It has a special name the way that you have it set up.
This next activity is great to use with something like a ball and a meter stick, or if your students are at home, maybe they have a lightsaber. How can I get this ball to orbit around me? So I can tap it along with my lightsaber, but is there a nice, easy way that I can get this to orbit around me without constantly tapping it on its side? Which direction should I give it a push on?
I found if you try and kind of like hit it.
Yeah, the marbles might be tricky.
Yeah, I think so. They're a little
Go
bit too
with
small.
the Angry Bird balls.
Actually knows what he's doing with this one.
That's the move.
You can do it
No,
faster.
you can move your feet too if you need to.
Oh, dang.
There we
See,
go.
hit it towards yourself. That's the move.
Well, I'm
Towards
getting
yourself,
really...
that is the move.
I knew it because you said the forces go towards the center or something earlier
Did I
this
say
year. I think
Oh,
so.
no, I didn't think anyone would listen to me. You can move your feet too if you need to. You can move your feet too.
Woohoo! And then you get to fence with Elijah once you're done.
No, you do not. You actually don't get to fence with anyone.
In the early 1600s, Galileo used the newly invented telescope to peer into space. What he found were 4 dots of light that seemed to be moving around Jupiter. He tracked them night after night, observing their positions and recording that in his notebook. What were those dots of light? Well, turns out they were Jupiter's moons. Galileo had discovered 4 moons of Jupiter, named Ganymede, Io, Callisto, and Europa. Those 4 moons were orbiting around Jupiter, and something that people had never seen before. Well, actually, the only moon we knew about at the time was our moon. So this was a big point in disproving the geocentric model of the universe and more support towards the heliocentric model. The lab that we're going to perform with this is useful for a physics class studying uniform circular motion or an astronomy class studying orbits. In this lab, we're going to replace our large central object, Jupiter, with a hanging mass on a string. We'll connect that to a spinning mass, which is orbiting around, and that's going to be something soft like test tube stoppers, so we don't poke an eye out. From there, students are going to adjust different variables, like the mass of the planet, the mass of the moon, and the orbital radius to determine what effect those have on the orbital period. The orbital period is how long it takes for the moon to complete one complete revolution around the planet. Let's look at how we set this lab up. For this experiment, you'll need string, scissors, a binder clip, a tube that's sturdy and hollow, so this is actually the tube that the string went around, hanging masses, a ruler, a meter stick, and something fairly soft that you can send a string through. Here I'm using test tube stoppers. To start this experiment, cut your string to length and then send one end through the cylinder. This is harder than it looks. Come on. There we go. On one end, we're going to attach the test tube stoppers, and on the other end, the hanging mass. You can see that's the hardest part of setting up this lab. So we'll just tie this on and make sure it's secure so that it's not going to fly away. Perfect. From there, you can measure out the desired radius of orbit. And that's what we want hanging out of this tube. So I've measured, just for demonstration purposes, this is 50 centimeters. So I measure 50 centimeters from the test tube stopper to the cylinder. And the way that I'm going to place the binder clip is just so that it is right below the cylinder so that this can't extend anymore. Safety always in the lab. So we have our hanging mass giving some downward force, creating tension in the string. This mass acts like Jupiter, and this acts like the moon around Jupiter. So we're going to hang on to this and then spin this test tube stopper. Once we have it spinning in a roughly horizontal circle around our head, our partner will time and tell us how many revolutions we have. So start the stopwatch, count 5 revolutions, and determine how much time that took. Let's see it spin. So you could see there, as I was spinning, if I was spinning too slowly, this would, the position of the binder clip would change. and it would start to fall down lower, like this. So at this, where I was holding here, this would start to fall down lower, so I could speed it up and get it to be just around the level of the binder clip. And if I was going too fast, they would touch. So the binder clip is an indication of whether you're going the right speed. And then once you've got the right speed, try to even it out so that it's pretty much horizontal. And then your partner can time how long 5 revolutions take. So that gives us some baseline data. Now to change the mass of the moons, students can add more test tube stoppers or whatever material they have at the end there that's not going to poke an eye out. To change the mass of the planet, they would add additional masses here to make it heavier. And the other thing that students can change is the orbital radius. So if your string is long enough, you can measure out a new distance and just move down the binder clip. So now students have a longer orbital radius. What your students should find is that the mass of the moon doesn't really affect the orbital period. The orbital radius does affect, and the mass of the planet absolutely affects the orbital period of the moons. So now they can apply that to some discussion questions at the end of the lab. If you go the inquiry approach to this, you can have students brainstorm ideas of what affects the orbital period. Some common answers would be the orbital radius. So we'll just place that around on a sticky note. The mass of the moon, or the mass of the planet. When setting up an experiment to test this, we can only test one of these at a time. So what I have my students do is bring the orbital period, which is the dependent variable, and select one of the other variables that they want to test, the one that they want to test first anyway. So let's suppose it's the orbital radius, and then we'll just move these stickies over, the mass of the moon and the mass of the planet. These will be kept constant. Now we can write a question, and we can write how are we going to keep these two constant. It's pretty easy to add the words how does the affect the question mark to create a question here. So how does the orbital radius affect the orbital period? Any leftover factors that could have affected the orbital period go on the right hand side, and now they're controlled variables. So how will we keep the mass of the moons the same, and how will we keep the mass of the planet the same? Students can write out the exact values that they're going to use if they're going to have this as an inquiry-based experiment. Sometimes when you're doing this, you'll find that students need to actually try it a few times to get an idea of what would be an appropriate mass for the moon and for the planets. If you have smart carts in your class, these are awesome because you can get a lot of information about the centripetal force just by spinning these around. Pretty simple. Take some string, tie it a few times tightly to the smart cart. After you connect to Spark View, what you'll do is whip it around. I take my students outside for this, and we change the radius, so we make it a tighter radius, and we also change the speed. From there we can see on the graph of force that it is really tied to the changes in speed and the changes in the radius.
This like stresses me out on like a fundamental.
This is my spinning plate apparatus. It's so simple. It's just a plastic plate from the dollar store that's sturdy, nothing too flexible. And 4 strings. On the back I just duct tape everything. So again, nothing fancy here. I've got the 4 strings meeting at a point, and then I just use my, whatever cups I have lying around the classroom. And I find this one easy to do outside because then I don't feel bad. One year, my thumb got caught on the string and I kind of lost control and it sent the water cup flying across the room. I think a few kids got some drops on them. So now I just do this experiment outside. I feel way more comfortable doing that, but it's pretty simple. Just fill up some water, put it on the plate, and start simply back and forth until you start to feel confident. I like to start in a vertical circle and then go full cowboy over my head. And then for dramatic effect at the end, you can take a sip of water, dump the rest out so the kids know that you weren't faking it all. There is water in here. Thank you. You may want to stand back. I have messed this up in the past.
You're in the way.
Okay. So far, no spilling.
Whoa. Physics.
Now what? Now what?
There's no water. There's no water.
Yeah, there is.
Drink out of it. Spit it.
Oh.
Okay. So far, no spilling.
No. All the way around. Pull the upside down. All the way around. There's no roller coaster.
Yeah. Now what?
This is
Now
gonna
what?
dredge.
Oh.
There's no water in that cup.
Yeah, there is. There is.
Drink out of it. Spit it. Oh!